Hi and welcome to Hacking with Python. In this episode we're going to explore one of the most prolific vulnerabilities out there. It seems to come up again and again and again, no matter the language, no matter the platform, people seem to keep making this mistake. In this episode we're going to do hands-on hacking of some applications. I'm going to show you the basics, I'm going to show you how to prevent them from happening, and then we're going to look at some advanced attacks that have happened in the wild, how they've worked, and what you can do with it. Let's get into it.
A really common way that people implement login forms is they have a database, and in the database they have two columns, one for the username and one for the password. I've got 4 demos here and I can show you how to bypass the login process. There's some example Python code here. This is really pseudocode, but it's saying, okay, this is probably what the Python is doing in the background to run a query on the database, compare either the username and password in SQL, or compare the username in SQL and the password in Python. Those are kind of like the two models that people typically use. And then this is what you would have on the client side. So the user would type in either an email address or a username. There's really kind of different models. It doesn't make any difference, to be honest. So if my username was anthony@domain.com, then down here you could see what the executed SQL query is. This is a sandbox. I'll put it in the notes at the bottom of the video so you can download this and have a play. You just need to use Chrome, and I've got some example injections you can use, and as you're typing it will show you what the SQL query is, and it will highlight the syntax as well. So it's quite a nice little sandbox just to kind of have a play around safely without breaking any laws. So there's a couple of things you need to note here. So in this example, this is probably the worst thing you can do as a developer, is to compare the username and password in SQL and just do it like this, so do it like a regular string replace, because I know that email addresses can't have apostrophes in them. The password could, and even if in the registration process you stopped the user from registering with a password that had an apostrophe in it, or vice versa for either the username or the email address, there's nothing to stop them from typing that in. So you can see if I put the string delimiter, depending on the database engine, the string delimiter could be a single quote, a backtick. But what I can do here is I can comment out the rest of the query. So you can see it's still going to be trying to parse the password. Just using dash dash is a line comment in SQL. This is a really common technique. So what will actually happen is when the query runs, it's going to give me the user that matches the domain that I typed in, or the username that I typed in. If this was the username instead, or admin's probably a better example, and you didn't know the admin password, you just do admin. If it was vulnerable to SQL injection, you could just put an apostrophe and then a dash dash, and it would just ignore the password component. So there's a couple of things that the developer might have done to kind of make this a bit more secure. One is that they might have encrypted the password in the database. That actually doesn't make any difference in this case, because the encryption would be done on the server side first using typically a salt, and then at storage, so in the database, the password would also be encrypted. So they're also doing the comparison in the SQL query, and because you've commented out the rest of the query anyway, it doesn't matter if the password is encrypted or not. So this is a way that you can get past encrypted passwords. And then a slightly more complex example, so hack number 3 would be where the username is compared in SQL and the password is compared in Python. So if this is still vulnerable to SQL injection, which this particular sample is, what people typically do when they write these code snippets is they say, okay, get the password from the database, from the user table where the username matches the one that they supplied. There's a couple of reasons people do this. One is that they don't want to have to deal with formatting passwords and stuff like that. And then they can compare the password in Python. So there's a way to get around this one again, using basic SQL injection, is you basically do a union query. So instead of getting the actual password, what you can do is you can return back a fake password, and that fake password is the one that you supplied on the form. So I've put a demo here because saved me kind of typing it out. But there's different ways of doing that. It depends on the database engine in the background. But this union query will basically select a fake password, and that will actually be the first field rather than the actual password from the database table. So it'll actually give you the string that comes back from the database. So the DB password will actually be fake password, and the username will still be admin. And then you can just type in fake password here. And then when you do submit, the comparison is going to pass because the form password is going to be fake password, and the DB password is going to be fake password as well, because you've done it in here. And then lastly, this one is a little bit more complicated because if they've done encryption, storage encryption in the database, and then they're doing a comparison of the password, then if you did do fake password, that's not going to work because it's going to encrypt what you typed in using their encryption algorithm, and then it's going to compare the encrypted version with the database version. The only really way to get around this one is if you can guess at what encryption tool that they've used. If people are vulnerable to SQL injection, it typically means that they are pretty slack when it comes to stuff like encryption as well. So you could probably guess like they're using a SHA tool, or they're doing, even like worse would be MD5 or something. When you do this union query, MD5 your password and try that first, and then put the actual like fake password in here, but do the hashed version in this segment, so that when it runs it and it compares it, you would try a couple of different hashing algorithms and see if any of those work. And odds are you can probably get through. There's otherwise that you can cause a bit of disruption. I guess the last one you can do is like a chained query. So the semicolon in SQL on most engines allows you to do multiple queries. Make sure that you end it in a double dash to just comment out anything else that might have been on the actual query, because you never know what other syntax is in there. But then using a semicolon, you can do like, an insert query, a delete query or something, or an update. So this requires you to know the table structure, which is a bit of a challenge. But if you've guessed already that the password field on the users table is called password, odds are that's probably the case, then you could probably just do an update on the target user. So you would do update users set, and then change the actual password in the database to your target password, and don't, and then that's another way of doing it. Or alternatively, you can create your own user using the same technique. One extra resource I want to point you to as well is the SQL Injection cheat sheet by NetSparker. This is a very comprehensive list of SQL injection examples, and it also does a comparison of what syntax works on which database engine. There's one in particular that I haven't covered off in this demo. Microsoft SQL Server in particular is vulnerable to a really dangerous set of SQL injection techniques. If you go down and have a look at the enabling XP CMD shell in SQL Server, this works in later versions of SQL Server as well. If the web application that you're targeting has the permissions to do so, you can enable this particular type of store procedure called XP CMD shell. This store procedure is so dangerous. Why this store procedure even exists on a database server, I still cannot fathom. But what it allows you to do is to run a store procedure that runs commands on the local server, the server that is running the database. So those commands can include things like changing registry keys, adding yourself as a user, adding yourself as administrator, turning off the firewall. You can pretty much completely own the machine just from SQL queries. So there's some examples on how to do that in here. Again, this should be used for testing purposes, but it talks you through how to do that, how to enable them, what some of the store procedures do. There's the registry, for example. There's the CMD shell. This is a really simple example of doing an exec on the CMD shell store procedure, and then just passing it the commands that you want to run, and they will be run on the server. By default, this is disabled, and if the server's been configured properly, that shouldn't even be possible, and the user that the database is being connected to, as from the website, shouldn't even have permissions to run these kind of store procedures. But the issue is that sites and applications which tend to have bad security practices, such as allowing SQL injection in the first place, that kind of stuff goes hand in hand with poor configuration on the database and poor permission setup. So it is likely that whoever created the database and set up the connections just ran a migration script from the web server. Migration scripts tend to require things like creating tables, dropping tables, and escalated privileges. So the odds are, in a lot of cases, they just run the website as admin on the database and they use an administrative user, which means that the CMD shell store procedures would work. They'd be turned off by default, but you can turn them back on anyway in SQL. And then you can run any of these store procedures to cause absolute havoc on the machine. Again, this is for testing purposes. Do not do this on something that you do not own or someone has not paid you to test. So the other hack I want to show you, I've added this in the sandbox as well so you can have a play around, is to do with the other way that web applications talk to the backend. And this is one that is typically easier to manipulate because developers don't expect somebody to interfere with the request. And that is when it comes down to Ajax. Ajax requests are really popular in modern web applications. So you have a JavaScript front end, which is making requests to the back end to get data, which makes the site more responsive. It means you can do things without reloading the page. So with Ajax, doesn't really matter what the JavaScript framework is, but I've just got a quick demo here. If you go ahead and open up the developer tools and then go to the network tab in Google Chrome and then click either of these two buttons, it will send two different requests to the backend. What the backend code might look like. So I just simulated like a simple product API. So maybe you filled in something or you added a product on the front end, and then the backend might say, okay, load the data from the post request and then run a SQL query, and you're going to say insert a new item into the database, and we're going to do ID, name, price, stock, and the actual query itself, the request, is going to contain that information. So if you're going to look inside that data, it has errored because this API doesn't actually exist. I just wanted to show you the Ajax component. If you go down to the bottom, you'll see that this is sent over form data. So the information here, ID, name, price, stock, is all over form data. The other product does it slightly differently. It uses JSON to do this, so it just stringifies the JSON request. Either one, let's pick the first using the post method. So just click on that, right click, do copy as curl. And there isn't a copy as Python, unfortunately, but there's a simple online tool. You can just go and paste that curl command in and it will convert that into Python for you. So just copy that out and open up a code editor. So if you just paste that in, it's going to copy across everything that your browser was sending to the backend when it made the Ajax request. And then you can basically go and manipulate any of these properties to try and see if you can find any SQL injection vulnerabilities. So first things first, it adds all the headers that the web browser was sending to the backend. These would include things like session tokens, your user agent string, which is the browser that you were using. Now, because you're attempting to do this using requests, if you don't provide the user agent, then it will actually say Python requests. If anyone's looking at the logs, it's going to be pretty obvious that wasn't a regular user because regular users don't use Python to communicate to the website. It's going to copy across any other kind of security properties or security settings that your browser was using. Keep in mind that if you do have a session, the backend will obviously know what the session was because you've just copied that across. So I've just put a fake one in here. But if you did have a session token, that can be associated to your login. So those headers and then the data get added to the post request. And then you can basically go ahead and do whatever you like with that information. So, but when it comes to things like numbers, especially if this originally was a number, for example, the price or the stock number, then if you went ahead and sent those as integers, I'm sure the backend would work properly. So if I go back to the example code, the insert query that the backend application possibly was using would be to wrap the name field in quotes because it's expecting a string. And then because the ID, the price, and the stock are not string types, they're not like the actual column type is not a string, then maybe the SQL query hasn't put those in quotes. So if you did use the single apostrophe and the double dash, that's actually going to cause a formatting error on the SQL query. Okay, so one example might be the stock property. So the stock property here is expected to be a number, and it hasn't been quoted at all in the SQL query. So one thing you could do in your script is, instead of sending a number as it was before in the initial request, is to actually just put raw SQL into that component. So you could either do that as a subquery, you could type a subquery in here. There's a couple of things that you're looking for in the response. First things first would be a 500 error. Isn't always a giveaway that something happened, but there was typically a problem in the backend. So whatever you've done to manipulate the data has caused an issue in the backend. If it does provide any information, whether that is through a stack trace or something, that's also going to be really helpful. So the response, if the response code is 500, then we're going to want to print out the response text. That's one thing we could look for. So if there is a crash, then print out the text. And if it does dump a stack trace, it's going to give you a lot more information about what happened on the back end, especially if their back end has been configured with debugger mode or any other kind of developer mode on it, which is going to be really helpful, give you lots of information. So try just typing garbage into any of these fields and seeing whether you can reproduce a 500 error on the back end. Something else we could look at as well is the amount of time it takes to actually execute the query. One other technique you can use is to actually just blindly test whether it's vulnerable to SQL injection by making the backend sleep for a certain number of seconds, and then timing the actual response time from the server and seeing how long it takes, and whether it was, typically a response time should be less than a second. So if you added a timeout of say 5 seconds or 10 seconds, then just timing how long that request takes. So the stock example would be a good one, because you can just type raw SQL into this. What we could do instead was, depending on the backend, so PG sleep is the Postgres SQL function for doing a sleep, and you could do a number of seconds in there and basically just run that as a subquery. So you could run a subquery to make the command sleep for 5 seconds, and then basically with the request to just time the request. So you would do a timestamp before the request and a timestamp after if it was longer, equal or longer than 5 seconds. All the different sleep commands for the different database backends are in the cheat sheet as well, if you want to check those out and try them with different parameters and different arguments. Okay, so what as a developer can you do to stop your code from being vulnerable to these sorts of attacks? So the basics are that you shouldn't mix raw user input with raw SQL queries. That's the basic principle. If you use an ORM tool like Django ORM, the Flask one, or SQL Alchemy, for example, the chances are it's done a lot of that for you. So it's escaped or sanitized the user input before it actually goes into a SQL query. But there are some edges to that statement. So it's not entirely true that if you use an ORM, you're actually safe from SQL injection. The other thing is you should be very careful when constructing SQL queries by hand and then mixing those, like I say, with input. One thing you can do just to do an audit of your code is you can use a couple of tools. One of them is Bandit, which is a free and open source tool which runs on the command line. The other is you can use a tool that I've written called Python Security, and it's a plugin for PyCharm. I've just got some examples open here. So this one here is vulnerable to SQL injection, and it uses the SQL Alchemy library. So it'll pick that for me and actually underline that and say, I've found potential SQL injection via the SQL Alchemy package, and it'll tell you where you've made those types of mistakes, because there are actually a few edges to the SQL Alchemy library that can cause this sort of thing to happen. If you were just typing raw SQL queries and using PsychoPG, for example, then it would just pick those out and underline those for you. So anytime you're doing any kind of string formatting, it would pick those out. If you're using the Django ORM and you ever use the user objects raw function, and you're using the raw function to actually run a raw query on the back end, again, the tool will find those for you. So you can either run that as a single audit on your project, you can run it from within PyCharm, or it's also available as a GitHub action. It will find those for you. Fixing SQL injections is critical. It is so important to make sure that you found these, you've squashed them all, and you've removed them. And like I showed you, this is not just on simple user forms like a login form or a request form, for example. There are other places your application could be vulnerable. Anything which takes an Ajax input is something you probably want to look into as well. Any other kind of back-end tools or back-end scripts, especially ones that are taking information from the database. Sometimes what attackers can do is they can put the SQL injection into the database, and then when it's fetched out of the database, it then causes the issue later on. So don't just assume that user input means anything that's taken from the web. It might also be any information that you fetch from a database or from any other kind of storage. So that is SQL injection in a nutshell. I really hope you enjoyed this episode. If you do, please subscribe. Please leave any comments. And if you want me to do more episodes like this, then please let me know.